Now we're going to finish off chapter 4, looking at section 4.5 and 4.6, which is primarily talking about some connectivity issues here. Now, if you don't have a diagram in front of you, or you have a very, very complicated diagram, it's all piled up or everything. Anyway, how do you tell if a graph is connected? We're going to develop an algorithm here that's called a DFS. For depth first search algorithm to come up with a spanning tree for a graph if it is connected. And I'm going to demonstrate on this little partial graph over here. The dot, dot, dot just means that there's more graph sticking out here that we don't really know what it looks like particularly. Okay, so here's our technique, our DFS technique for coming up with a spanning tree for a graph. Okay, so let's suppose the graph G has n number of vertices. Okay, so pick one of them. Doesn't matter if you don't have any preference for it, then pick any. And we're going to label it 1. So let's pick this guy right here. We'll call it 1. Now, this is an algorithm, so I'm going to describe a step-by-step process and for doing this. Then the next thing we want to do is to pick any vertex adjacent to this guy and label it as 2. So let's pick this one up here. We'll call it 2. Okay. In that case, we want to mark the edge 1, 2, since I don't want to use it. Okay, I've used it once. I don't want to use it again. So let me just put a little dash mark on it. Okay, next thing, pick any vertex adjacent to 2. And label it 3. And we mark the edge 2, 3. Okay, so I'm going to pick this guy as 3. We're going to mark that edge 2, 3, since I don't want to use that again. Okay, so this is the process. We just go pick any vertex to start. Okay, any adjacent vertex is the next one and mark that edge. Any adjacent vertex is the next one. All right, now if you look at what's going on at 3, I don't have any vertices adjacent to 3. So let me put out the general step here, and then I'll come back and handle that. So suppose we have a vertex V sub I has label has been given the label, say, K. So I've made like K number of decisions through here. I picked this guy up here. Okay. Then what we do is to pick any vertex adjacent to K. Okay, let me rephrase that. Any adjacent vertex and label that's not already chosen. Not already labeled. And and call it k plus 1. So 2, I picked this vertex and I called it 3. And mark the edge from k to k plus 1 so that we don't use it again. Keep this up. Now, what happens when we get to something like 3 that's out here on an end by itself? If you get to a vertex that has no unlabeled adjacent vertex, no unlabeled adjacent, okay. My handwriting is deteriorating, isn't it? Has no adjacent unlabeled vertex at from K, then what you want to do is to back up one step. Back up to the previous can't spell either. Labeled vertex. Okay. And go through the process. Excuse me. Back up to the previous labeled vertex. Okay. Pick any unlabeled adjacent vertex and call it k plus 1. Man, I really can't write. Right. So here I am at 3 up here, vertex 3. There are no unlabeled adjacent vertices at 3, so I back up to 2. Okay, and at this point I see that here's an unlabeled adjacent vertex, so I'll label it 4 and mark that edge from 2 to 4, and I don't want to use it again. Where 4 is, there are no previously unlabeled vertices, so I'll back up to 2. Well, at 2, I have no unlabeled vertices, so I back all the way up to 1. And at 1, I see that I have this unlabeled vertex. I'll call that 5 and mark this off. And at this stage, I would back up to 1 and head off in this other direction. Okay, so you keep this up when necessary, backing up. So continue until all vertices are labeled. Or until you've had to back up to 1 and you can't go any further. You get stuck, back at 1. Okay. If everything is labeled, if all vertices are labeled, okay, then you've got a connected graph and you've constructed a spanning tree for the connected graph. The marked edges are a spanning tree. Okay, if all the labels, if all the vertices aren't, if there's an unlabeled vertex or one or more of those, then it's not connected. If one unlabeled vertex. Okay. Well, I hope you understand what I said, because you sure can't understand what I've written. What I'd like to do as an example is, this is one done in the book, but I'm going to start it in a different way here. Okay, I want to, and this is a DFS spanning tree when we get this done. Depth first search. Okay, so let's work with this guy here. Process. Pick any vertex and call it 1. I'm going to pick this one down here. Okay. Now, look at all the vertices adjacent to it. Pick any of those and call that 2. And I'm going to go to this one in this spot. And let's mark the edge that connects those two, because I don't want to travel that edge again. All right, now from 2, I look for any adjacent vertices that haven't already been labeled. So there's 2 of them. Pick one and call it 3. So let's call this guy up here to the right 3, and let's scratch that label, that edge, because we don't want to travel along that edge again. Now from 3, pick any adjacent vertex that has not already been labeled. Okay, so there's this one, or this one, or this one. And pick one. I'm going to pick this one. I'm going to call it 4. Mark that edge. From 4, pick any adjacent vertex that hasn't been labeled. Well, there's only one, and that's this one over here, so we call that 5. From 5, pick any adjacent vertex that hasn't been labeled. Well, there's only one. That's this one down here in the lower left. Oops, I forgot to do that. Call that 6. At 6, pick any adjacent vertex that hasn't been labeled. There aren't any. So back up to 5. Pick any adjacent vertex that hasn't been labeled. There aren't any. Back up to 4. Pick any adjacent vertex that hasn't been labeled. There aren't any. Back up to 3. Pick any adjacent vertex that hasn't been labeled. Okay, there's a couple here. We'll call this one, let's see, 6. This one's going to be 7. Okay. There aren't any adjacent vertices to 7, so I'll back up to 3. And there's an adjacent vertex that hasn't been labeled yet. That's this one down here. We'll call that 8, and we'll mark that. Okay, so what we've done is we've labeled our vertices, and we've formed a spanning tree of the marked edges. So it goes 1 to 2 to 3. Okay, this is an acyclic graph. It's a tree. Okay, and this is a depth first search spanning tree. Different from the book because we started in a different place and we made our decisions differently, but it's one nonetheless. Now, I don't write programs, but I think you can see how to write a program, perhaps, given an abstract graph, that is just a set of points and edges here. We have a way of constructing this. So this algorithm is something I think it's a decision-making algorithm. The book talks a little bit about complexity here, which would be a really good topic for someone to research, because there's a limited number of decisions that have to be made. So you can estimate the total number of decisions, the maximum number of decisions that might have to be made in such an algorithm. Okay, so that's basically section 4.5. We'll take a look at the next section, which is on strong orientations. Now, first, I want to restate a theorem that was not proven. Okay, and it says a graph G is strongly connected. Excuse me, not strongly connected. I want strongly oriented. Okay. If and only if it is connected, it has no bridges. Okay. What that means is we could take this graph and give it a strong orientation, make it into a digraph where each vertex is connected to every other vertex. Okay, so the question we're going to investigate in this section is, how do we come up with a strong orientation? How do we find a okay? And the question, the way the book poses it, is suppose you had a city that was nothing but two-way streets, and you wanted to make all the streets into one-way streets. How might you do that? Yeah, this doesn't necessarily come up with the best way to do it, or the something that's wouldn't have a terrific traffic problem. But let's come up with one, and it's a two-step process. The first step, use our DFS technique to construct a spanning tree. Well, I'm going to do more than that. I want to label the vertices and construct a spanning tree. Okay, here's my example, this partial pentagon thing here. So let's start. I'm going to label this one as 1. Okay, so starting at this, I pick any of the 1, 2, 3 adjacent vertices, okay, and call it 2. And I'm going to pick this one up here as 2. All right, and let's mark that edge. Okay. Now from 2, I pick any adjacent vertex that hasn't already been labeled, and there's 1, 2, 3 of those. And I'm going to pick one of those and label it 3. I'll pick this guy up here. It doesn't matter. Label that 3, and let's label the edge there. Okay, mark it because that's the process. Now from 3, I pick, there are 2 adjacent unlabeled vertices. Pick either one of those and label it 4. I'm going to pick this guy, and that's the edge that gets marked. From 4, well, I can't, there aren't any unlabeled vertices from 4, so I back up to 3, and the only unlabeled one here is this guy over here, 5, and I mark that edge. Okay, so I've got my spanning tree and marked edges. Okay, now here's how we make our decision as to construct an orientation, to make a digraph out of this. So let's suppose that IJ is a marked edge in my spanning tree with I less than J. construct this, in other words, convert this edge to an arc from I to J. Okay, so 1, 2 is a marked edge. Okay, 1 is less than 2, so I'm going to change this. Let's see if I can do this. To a directed edge from 1 to 2. Okay, 2, 3 is marked. Okay, 2 is less than 3, so I'll change this edge from 2 to 3 into an arc from 2 to 3. The edge joining 2, 3 is now an arc. Okay. 3, 4 is a mark. The edge connecting 3 and 4 is marked. 3 is less than 4, so I'll make this into a, for some reason. No. A directed edge. Okay, 3, 5 is a marked edge, and 3 is less than 5, so I'll change the edge connecting 3 and 5 to an arc from 3 to 5. Okay. Now, let's look at the other guys. If IJ is an unmarked edge with I less than J, convert this into not an edge, an arc, not an arc, but the arc. From J to I, so go backwards here. Okay, so the edge between 2 and 5 is unmarked. 2 is less than 5, so I will go not from 2 to 5, but from 5 to 2. Okay, the edge 1, 5 is unmarked. 1 is less than 5, so I'll go not from 1 to 5, but from 5 to 1. Okay. 2, 4 is unmarked. The edge from 2 to the edge from 2 to 4 then needs to be changed to an arc going not from 2 to 4, but from 4 to 2. Okay. 1, 4 is unmarked, so I need an edge here not from 1 to 4, but from 4 to 1. Okay, now I'm not going to go through to justify everything here that this is a strong orientation, but let's just do a few of them. For instance, how do you go from, say, 1 back to 1? Let's go from 1 to 4, excuse me. Okay, from 4, I'd go 1 to 2 to 3 to 4, so I'd go that way. Of course, from 4 to 1, I just take the single arc that goes from 4 to 1. Okay. So if I'm going like 5 to 4, I would do 5 to 2 to 3 to 4. And you can show with just listing on down that it's possible to go from any vertex to any other vertex. So there's an example of how you put a strong orientation on a suitable graph. Okay, now if you the first section here talks about connectivity, which is a very interesting topic when it comes to graph theory. We're just looking at whether graphs are connected or not. But there's a whole range of things you can talk about as to how connected is a graph. In other words, if you have a graph, how many edges, what's the minimum number of edges you can remove before you disconnect something? Or what's the minimum number of vertices you can take out in order to disconnect the graph? So there are ways of measuring connectivity based on that, how many vertices you have to remove or how many edges you have to remove. It's a very interesting sort of topic. If you get a chance, I urge you to take a course in graph theory. It's a lot of fun.